The world of modern firearms manufacturing sits at a strange crossroads where industry, politics, culture, and ethics meet. Walk into that world and you will find more than machines and metal. You'll find designers balancing legacy and innovation, assembly lines mixing automation with careful human hands, compliance teams dealing with a thicket of laws, and a marketplace that is as much about identity and hobby as it is about commerce. The Ar-15 in particular has become a symbol, simultaneously a technological archetype, a cultural flashpoint, and a massive commercial product. Exploring how that industry operates, weighed without offering technical instructions or operational detail, reveals not only how factories function at a broad level, but why the conversation around them is so heated. The Ar-15 began its life as a lightweight, modular rifle design, introduced in the mid-20th century and later adapted into countless variations. Over decades, it was refined by manufacturers and users, and its modularity made it unusually adaptable. Different barrels, stocks, triggers, and accessories could be fitted for different roles. That adaptability, the ability to upgrade, customize, and accessorize, is a large part of why certain families of rifles captured so much of the civilian market. But the story of a factory making this product is less about the gun's mythos and more about the practical realities of sourcing components, maintaining quality and safety, meeting regulatory requirements, and serving customer demand. A modern U.S. small arms factory is rarely the movie image of secretive men hunched over benches. It is an industrial operation subject to many of the same pressures as any other manufacturing sector. Supply chain constraints, workforce management, cost efficiencies, quality systems, and customer relations. The facility will typically be divided into functional zones: design and engineering, parts fabrication, if the company makes parts in-house, sub-assembly stations, final assembly, finishing and surface treatment, inspection and testing in a strictly controlled sense, warehousing and shipping. Some companies vertically integrate, producing barrels, receivers, or electronic modules in-house, while others are assemblers, sourcing many components from specialized suppliers. These strategic choices shape capital expenditures, workforce skills, and regulatory exposure. Design teams in these companies often consist of engineers and product managers who translate customer expectations and legal constraints into marketable models. They do not write secret blueprints in the shadows. They respond to consumer trends, perform durability modeling, consider ergonomics and materials decisions, and think about manufacturability. The engineering work sits at a high level. What materials meet cost and performance goals, what geometries deliver reliability across conditions, and how to design parts so they can be produced and inspected consistently. This is industrial design rooted in practical realities, not a manual for construction. Sourcing components is a major piece of the puzzle. Factories buy steel, aluminum, polymers, springs, fasteners, optics, and electronic modules from a global network of suppliers. Each source has its own cycle and risk profile. Pricing volatility for metals, lead times for semiconductors and sensors, shipping disruptions, and geopolitical constraints. Recent years' events, trade disputes, pandemic disruptions, and semiconductor shortages have highlighted how sensitive even this industry is to global supply chain shocks. Some producers maintain relationships with domestic suppliers to reduce geopolitical risk. Others rely on specialized overseas vendors for cost or unique capabilities. Supply chains are managed carefully because delays or inferior materials can affect product reliability and business reputation. Regulatory compliance shapes nearly every aspect of production. Federal agencies, notably the Bureau of Alcohol, Tobacco, Firearms and Explosives, ATF, maintain oversight of manufacturers through licensing, record-keeping, and inspection regimes. There are also state and local regulations that vary widely. As a result, manufacturers assign significant resources to legal and compliance teams that ensure proper paperwork, traceability, and adherence to changing rules. Compliance goes beyond forms. It informs product choices, what features are legally permissible and in which markets, distribution strategies, how products are marketed and to whom, and export controls. Because the regulatory environment changes in response to policy and court decisions, manufacturers must maintain agility in their product strategies. Quality control in firearm production is rigorous in principle, not because of an industry pet peeve, but because failure has severe consequences for safety and legal exposure. Factories maintain inspection regimes, calibration schedules for equipment, and documentation for deviations. Components are typically subject to dimensional checks and visual inspections. Assemblies are verified to meet tolerances, and finished products are verified for function in non-operational ways that confirm fit and functionality without divulging technical procedures. Companies often pursue third-party certifications for their quality management systems, such as ISO standards, to standardize processes. The aim is to produce consistent products that perform as intended under normal use and to have records proving that due diligence was followed. Workforce issues are a human story often overshadowed by political headlines. Skilled machinists, assemblers, quality engineers, logistics staff, and safety officers make up the factory workforce. Many workers are proud of their craft. They take satisfaction from precision work, from hitting tolerances and seeing a final product that reflects their skill. The industry has a wide age range in its workforce. Some older craftspeople bring decades of experience. Younger workers are often attracted by the combination of technical skill and steady wages. Training programs, apprenticeships, and safety certifications are common. Workplaces invest in safety training and personal protective equipment to reduce hazards like noise, material handling injuries, or exposure to chemical processes used in finishing and cleaning. Automation is present but rarely total. CNC machines, automated machining centers, robotic material handling, and surface treatment lines increase capacity and repeatability. But many assembly tasks and finish inspections still benefit from human judgment. The human eye and touch remain critical for nuanced inspection and troubleshooting. The interplay between automation and manual skill defines the factory floor rhythm. Machines do the heavy repetitive tasks. Humans handle integration, quality assurance, and complex assembly steps. The industry also has an aftermarket ecosystem that supports customization, maintenance, and repair. That market is comprised of accessory makers, optics producers, parts distributors, gunsmiths, and retailers. This aftermarket is among the reasons the platform became widely adopted. Consumers can personalize ergonomics and performance, and a vibrant accessory market adds revenue streams beyond the initial sale. From a business perspective, these accessories are profitable and often less regulated, but they also raise questions about traceability and the life cycle of products once sold. Public debate around the Ar-15 family and similar firearms is not confined to technical details. It is deeply moral and political. Tragic high-profile shootings have focused public attention on the availability of certain types of firearms, on how marketing may influence use, and on how the legal framework balances individual rights with community safety. Manufacturers, advocacy organizations, legislators, and advocacy groups on both sides are engaged in ongoing, often polarized dialogue. This debate influences policy, consumer sentiment, and corporate risk assessments. Some manufacturers have responded by emphasizing safety programs, community engagement, and worker development, while others focus on continuing to serve a customer base that values self-defense, sport shooting, and collecting. Corporate social responsibility has become a more visible element of the sector. Some companies invest in training programs that promote safe storage, safe handling, and conflict avoidance education. Others partner with hunters associations, law enforcement training centers, and charitable organizations. Consumer education campaigns about storage and responsible ownership are part of many firms' public relations strategies. At the same time, critics point out that corporate messaging cannot fully offset real-world harms if products are misused, and they press for policy changes to tighten oversight or restrict certain features. The tension between corporate outreach and public safety concerns is a recurring theme in conversations about the industry. Economic dynamics matter too. The firearms industry is influenced by macroeconomic cycles, consumer confidence, and the political calendar. Sales often spike in response to certain political events or legislative proposals, reflecting how consumer behavior mixes practical demand with symbolic action. Market segmentation is broad. There are consumer lines focused on affordability, premium custom builders who cater to collectors, defense contractors supplying law enforcement, and accessory makers that serve enthusiasts. Pricing strategies balance material costs, labor, and desired margins. Financing, retail distribution, and online sales channels affect how products move from factory to customer. Innovation does not only mean more powerful products, it includes improved material science that increases durability without compromising safety, ergonomic advances that reduce user fatigue, and electronics that enhance non-lethal features like training aids or inert simulation rounds for safety training. Some companies invest in research on reducing accidental discharges, making safeties more intuitive, and improving storage technologies. There is a growing interest in smart technologies designed to prevent unauthorized use, though these innovations also raise questions about reliability, privacy, and consumer acceptance. The global dimension cannot be overlooked. Export controls and international regulations limit where certain products can be sold. Manufacturers that operate globally must navigate foreign regulatory environments, export licensing, and political sensitivity. Arms trade is an area of close government oversight because of its potential implications on regional stability. Multinational firms develop compliance programs for international law and differing national standards, which complicates supply chains and market planning. Ethics and community impact are at the heart of public scrutiny. When a factory operates in a town, it brings jobs and tax revenue, but it also introduces a product that has clear potential to cause harm if misused. Local communities, company leaders, employees and their families, public health experts, and victims advocates all inhabit the same moral landscape. Companies sometimes attempt to bridge divides by hosting community forums, supporting local education programs, and funding research into prevention of misuse. Yet many critics call for stronger regulatory action, better enforcement, and cultural shifts in how firearm ownership is discussed and normalized. One particularly thorny topic is the issue of unregulated, homemade, or ghost weapons, and how they intersect with factory-made products. The existence of untraceable or minimally regulated devices has catalyzed legislative and enforcement debates as policymakers weigh technological freedom against public safety. Manufacturers generally caution against illegal modifications and emphasize responsible ownership, but the broader debate often shifts quickly into questions about enforcement, technology controls, and civil liberties. Media framing affects public perception heavily. Coverage that highlights sensational incidents can shape policy discussions and investor sentiment. At the same time, thoughtful journalism that examines supply chains, workplace conditions, regulatory frameworks, and community impacts can produce more nuanced understanding. The industry, therefore, faces a dual challenge. It must manage the very real business of production while responding to an environment where public opinion can influence sales, regulation, and long-term viability. Finally, the human cost, the stories behind statistics, demands attention. There are workers who find pride in their craft in communities that depend economically on factories. There are customers who see ownership as a hobby or a constitutional right, and there are victims and survivors whose lives have been irrevocably altered by misuse of firearms. Any responsible documentary view of this industry has to honor that human complexity, to neither demonize every worker nor ignore the suffering caused by abusive uses. If you step back from the machinery and the policy debates, the picture that remains is one of an industry embedded in larger social structures. Factories produce objects that are legally owned by citizens, used in sporting contexts, and sometimes tragically misused. How society elects to regulate, educate, and design for safety will determine how those factories' products live in the world. The core questions extend beyond manufacturing. What balances of rights and responsibilities do we accept as a society? How do we support innovation without undermining safety? What obligations do companies have, economically and morally, to the communities they affect? For viewers curious about what's happening on the ground, the day-to-day reality is often more mundane than the headlines. Teams troubleshooting supplier delays, compliance officers updating protocols in response to new guidance, machinists solving assembly issues, customer service reps handling warranty claims, and engineers iterating on designs to improve ergonomics or reduce manufacturing cost. This daily grind is where policy, ethics, and commerce intersect in practical ways. It's also where changes can have a measurable impact. Better worker training, more robust compliance, improved storage education, and community engagement can all reduce harm without suppressing legitimate lawful uses of products. Conversations about the industry will continue to be contentious because they are rooted in deeply held values, but factual, careful, non-sensational discussion, the kind that looks at economics, regulatory detail, workplace safety, and community impact, can help move public debate from polarized slogans to pragmatic solutions. There are no simple answers. There are trade-offs, hard moral choices, and policy levers that produce different kinds of outcomes. A documentary approach that centers people, context, and evidence offers the best chance for constructive discourse. If this look inside the industry sparked questions for you, consider digging deeper into public records, regulatory documents, and balanced reporting from a mix of sources. Read perspectives from workers and managers, victims advocates, public health researchers, and policy analysts. The issue is complex, and understanding grows from exposure to many different viewpoints. If you found this is the story of the B-2 Spirit, the most secretive, most expensive, and most technologically advanced bomber ever built. When people say stealth bomber, this is what they mean. The B-2 didn't just redefine aerial warfare. It redefined what engineering can achieve when politics, innovation, and dollars meet in perfect shadowy chaos. It all began in the grim early days of stealth research. Back in the 1970s and 1980s, Cold War tensions were high, and the U.S. military needed something that could penetrate enemy radar defenses undetected. Enter the Advanced Technology Bomber ATB project. From the moment Northrop Grumman took the prime contractor role, they knew they were building more than a plane, they were building the future. The manufacturing story of the B-2 is a tale of materials, secrecy, and scale. Unlike traditional aircraft, this one was almost entirely molded from carbon fiber composites. More than 10,000 composite parts, graphite epoxy skins, and honeycomb structures formed a single flowing flying wing skin, strong enough to house engines, crew, and weapons, yet light as a whisper. The only exceptions were titanium used in internal beams and engine compartments. To build such a masterpiece, Northrop couldn't rely on off-the-shelf tools or factories. They had to invent the entire process. Hyper-specialized molds, software systems, three-dimensional modeling, a manufacturing ecosystem where even the smallest misalignment could jeopardize stealth. Workers described the B-2 line as a place of rigorous discipline. Every move monitored, every step controlled for absolute precision. A slip meant weeks of recertification. The bomber's iconic flying wing shape, first envisioned by Jack Northrop as the YB-49 in 1949, was reborn in carbon fiber for stealth. By eliminating a tail, vertical stabilizers, and radar reflective surfaces, the B-2 dramatically lowers its radar cross-section, making it appear like a tennis ball on enemy radar screens. That stealthiness is also achieved through special composite coatings, infrared masking, sound-dampening materials, and precise shaping to reduce all radar, visual, heat, and acoustic signatures. Even the test range was classified. Northrop built the Tejon Ranch Radar Cross-Section Facility, hidden deep in the Antelope Valley, to measure how different surfaces reflected radar. Aeroforms were mounted on rotating turrets and bombarded with radar energy to tweak their shape until they became invisible enough to pass and fly. All of this secrecy cost money. Initial estimates envisioned 132 B-2s, but as complexity mounted, the Cold War ended and costs soared. The number dropped to just 21. Each airplane ended up costing over $2 billion when adjusted for inflation, making it arguably the most expensive aircraft in history. The total program bill soared to $44 billion or more, around $13,000 per pound of aircraft. Production was centralized at USAF Plant 42 in Palmdale, California. Major sections came from 250 subcontractors across the UAs, then shipped and assembled in secret behind fences and armed guards. The first flight took place in July 1989. Production wrapped around 2000. The B-2 carries 4 General Electric F118-GE100 turbofans chosen for low infrared signature and efficient subsonic performance, a perfect match for a stealth bomber that prefers invisibility over speed. Beyond the stealth and structure, the bomber's systems were equally complex. It features dual rotary bomb bays that can rotate and deploy up to 40,000 pounds of weapons, either conventional JDAMs or nuclear B-83s, all triggered by computerized automation to reduce radar exposure time. But building relic-like perfection isn't enough. Maintaining it is a different beast. Each hour the B-2 flies demands 119 hours of maintenance, double the B-1's needs and more than double the B-52's, thanks mainly to its stealth coatings and delicate composites. Weather-controlled hangars that cost $5 million per unit are needed just to house it, adding to its yearly operating cost of over $30 million per plane. Maintenance yards perform depot-level refreshes roughly every 9 years, involving massive restoration, especially of low observable surfaces. Despite the costs, the B-2 can reach anywhere in the world, with a range of about 6,000 nautical miles unrefueled and the ability to carry both conventional and thermonuclear weapons. It emerged as a symbol of U.S. strategic power and deterrence during and long after the Cold War. The bomber has seen combat, notably in Kosovo in 1999, demonstrating its value in precision strikes. 2 aircraft flew a 15-hour mission, refueled mid-air, and hit targets undetected. However, the B-2's history hasn't been without drama. In 2008, Spirit of Kansas crashed in Guam during takeoff due to moisture and air sensors, triggering a stall and ground impact, resulting in a $1.4 billion loss. A sobering reminder that even the most sophisticated machines remain vulnerable to small failures. The bomber continues to fly, maintained by Northrop and the USAF. In fact, in 2024, depot maintenance on B-2s was completed 91 days ahead of schedule thanks to advanced pre-inspection planning and prioritizing fuel system inspections, reducing delays and cost. Looking ahead, the BB-21 Raider is set to succeed the B-2, developed at the same Palmdale facility. It promises updated stealth, automation, and cost control, hopefully avoiding the B-2's tumultuous cost trajectory. Yet, today the B-2 remains unique. 20 aircraft for a $23 billion program, including development, production, and upgrades, means each plane represents a pinnacle of Cold War-era ambition and engineering resolve. In the quiet assembly halls of Plant 42, pieces of carbon fiber join together under strict controls, marching toward becoming the silent ghost over enemy skies. Each bomber may be rare, but together they embody a philosophy that sometimes the highest price delivers not extravagance, but the power of the unseen. But here's the part that really blows minds. The B-2 isn't just about its airframe or radar-absorbing skin. It's about the integration of systems that make the entire aircraft act like a living, breathing organism. Every sensor, every computer, every hydraulic pump, and every software line works in harmony. The plane was built not only to hide, but also to think faster than its enemies. Engineers say the B-2's onboard computer systems were decades ahead of their time, capable of processing signals, countering enemy radar sweeps, and adjusting its stealth profile in real time. That's why pilots often compare flying the B-2 to being part of a symphony. Every element comes together seamlessly to create something greater than the sum of its parts. One often overlooked part of the bomber's design is its maintenance. Unlike older aircraft, which could be rolled into a hangar and worked on by just about any airbase crew, The B-2 requires its own highly specialized climate-controlled shelters. That radar-absorbing coating? It can't be left exposed to random desert sand or humid air. Every tiny scratch or imperfection can compromise stealth. This means the Air Force invested in creating high-tech facilities just to house and service these bombers. It's one of the reasons the B-2 costs so much per flight hour. Every mission requires a delicate choreography of preparation, care, and post-flight work. And let's not forget the human side of this. The B-2 is flown by a crew of just 2 pilots, but the support behind them is staggering. From mission planners to ground maintenance teams to stealth coding specialists, each flight involves hundreds of hands making sure everything works exactly as it should. Pilots often undergo years of training before they're even trusted to sit in the cockpit. Because flying a B-2 isn't just about navigation or weapons delivery, it's about managing one of the most complex aircraft ever conceived. Veterans describe the experience as both exhilarating and exhausting. There's no room for error because a single mistake can compromise billions of dollars of technology and decades of strategy. But here's the fascinating irony. This symbol of advanced technology, this marvel of human engineering, is largely invisible. Its missions are rarely publicized. Its flights often go unreported. Even when the B-2 deploys, it slips in and out without anyone knowing until long after the fact. Unlike fighter jets that roar across the skies or transport aircraft that carry humanitarian aid, the B-2's story is one of silence and shadows. And that's exactly what it was built for. To remind adversaries that no matter how strong their defenses, there's always a ghost lurking in the skies above. Over time, the B-2 has also become a political tool. Its flyovers at major events are not just military demonstrations, they're subtle warnings, projections of power designed to remind allies and enemies alike of what America is capable of. When a B-2 glides silently over a stadium during a national holiday, it's not just showing off, it's sending a carefully crafted message that this aircraft is both a guardian and a deterrent. That symbolism is priceless, even beyond the billions spent building and maintaining it. Of course, the program wasn't without controversy. Critics have long argued that the B-2's astronomical price tag outweighed its benefits. With only 21 bombers ever built and billions sunk into research and production, many questioned whether America could have invested that money into more practical aircraft or even non-military projects like healthcare and infrastructure. But supporters counter that the bomber's very existence prevented wars from escalating. If adversaries knew the U.S. had a weapon capable of striking anywhere in the world undetected, they might think twice before provoking conflict. In that sense, the B-2 wasn't just a war machine, it was a silent peacekeeper. And then there's the evolution of technology. When the B-2 was first unveiled, it seemed almost alien. But today, as newer projects like the B-21 Raider emerge, the question arises, has the B-2 already outlived its prime? The Air Force insists the bomber will remain relevant for decades, especially with ongoing upgrades in avionics, communications, and stealth coatings. In many ways, the B-2 serves as the blueprint for the future of stealth. The lessons learned from its design and maintenance are now guiding the next generation of aircraft, proving that the B-2 wasn't just a weapon, it was a stepping stone toward the future of aerial warfare. What's even more remarkable is how the bomber's existence reshaped global military strategies. Nations around the world took notice. Russia invested in more advanced radar systems, while China pushed forward with its own stealth projects. The ripple effect of the B-2's introduction was felt everywhere, sparking a new arms race centered not around numbers, but around invisibility. The bomber changed the game by showing that air superiority wasn't about how many aircraft you had. It was about who could remain unseen the longest. Still, despite all the secrecy and innovation, the B-2 has had its share of vulnerabilities. In 2008, one of the bombers, the Spirit of Kansas, crashed shortly after takeoff in Guam due to a maintenance error. While the crew ejected safely, the incident highlighted how even the most advanced machines are only as strong as the humans operating them. That single crash represented not just the loss of a $1.4 billion aircraft, but also a reminder that perfection in aviation is a myth. Every system, no matter how advanced, has limits. Yet, despite its challenges, the B-2 remains unmatched. Even today, no other country possesses a bomber with the same combination of range, payload, and stealth. And perhaps that's why it continues to captivate imaginations worldwide. It's not just an aircraft, it's a symbol of ambition, ingenuity, and the relentless pursuit of dominance in the skies. As the world looks toward the future, with drone swarms, hypersonic missiles, and AI-driven warfare on the horizon, the B-2 still soars as a reminder of what happens when humans dream big and refuse to accept limits. Built in secrecy, refined through innovation, and tested in the crucible of global politics, the bomber represents the height of Cold War determination and the dawn of a new military era. And in the end, that's the real story of the B-2. It's not just how it was made in factories with specialized coatings and titanium bolts, it's about why it was made and the world it helped shape. One of the more fascinating aspects of the B-2 is how it has remained relevant for over 3 decades in service, despite rapid technological shifts in warfare. When it first flew in the late 1980s, the internet was in its infancy, GPS was not yet widely available, and precision-guided munitions were still evolving. Yet the bomber was designed with adaptability in mind. Engineers ensured that the B-2 could be upgraded with new avionics, sensors, and weapon systems, meaning the same aircraft that once carried unguided bombs in the 90s can now deliver cutting-edge precision strike packages. This foresight is one of the reasons why the B-2 hasn't been retired yet. It was built to grow with technology, not be left behind by it. Thanks for watching, and I'll see you in the next mission. If you enjoyed this video, don't forget to hit that like. A small piece of uranium about the size of a grape has the power to generate enough energy to light up an entire neighborhood for a year. That might sound almost unbelievable at first, but it sparks the question, how can something so small contain such enormous power? The journey of enriched uranium is not just a story of science, it's a story of history, engineering, discovery, and the shaping of the modern world. To understand it fully, let's take a deep look at how this rare and dangerous metal is mined, processed, transformed, and finally used to power cities across the globe. The story begins in the late 19th century, when uranium wasn't considered particularly special. It was in 1896 when French physicist Henri Becquerel made an astonishing observation. Uranium emitted invisible rays all on its own, without sunlight or any external source. This was the birth of radioactivity as a concept. His work inspired Marie and Pierre Curie, who dedicated their lives to studying these strange emissions and discovered entirely new elements like radium and polonium. Just a few decades later, in 1932, James Chadwick identified the neutron, a subatomic particle that would prove critical to unlocking nuclear energy. Then in 1938, Otto Hahn and Fritz Strassmann, with vital input from Lisa Meitner and Otto Frisch, demonstrated something that seemed almost like science fiction. A uranium atom could split in two when struck by a neutron, releasing a burst of energy far greater than anything seen before. This process became known as nuclear fission, and from that point forward, uranium was no longer just another mineral. It became the key to an entirely new form of energy. But there was a complication. Natural uranium mostly contains uranium-238, about 99.3% of it in fact, which does not easily undergo fission. Only a tiny fraction, around 0.7%, is uranium-235, the isotope that makes nuclear energy possible. To make uranium practical for reactors or weapons, the amount of uranium-235 must be increased. This process is called enrichment, and it quickly became one of the greatest scientific and technical challenges of the 20th century. During the Manhattan Project in World War II, scientists pioneered the first methods. They tried gaseous diffusion, which forced uranium gas through thin membranes so that lighter isotopes could be separated, and electromagnetic separation, which bent ionized particles through magnetic fields to pull apart isotopes. These worked, but they were slow and devoured enormous amounts of energy. In the 1950s, a breakthrough came with the invention of the gas centrifuge, a machine capable of spinning uranium gas at staggering speeds and separating isotopes with far greater efficiency. These devices became so critical that their blueprints were guarded like national treasures, considered state secrets by governments around the world. What made enrichment such a turning point was that it shifted uranium from being just a scientific curiosity into a practical source of controlled power. The ability to enrich uranium-235 meant that reactors could be designed with predictable outputs instead of unstable reactions. It also allowed governments to unlock the enormous destructive power of nuclear weapons, changing global politics forever. The very idea that spinning cylinders of metal invisible to the public eye could determine the balance of power between nations gave enrichment a near-mythical aura. Engineers working on these systems often describe the centrifuges as temperamental giants capable of incredible precision but unforgiving if mishandled. Even a small technical flaw could bring an entire cascade of machines to a halt, yet when operating smoothly, they represented one of humanity's greatest engineering achievements, blending chemistry, physics, and high-strength materials into a single system. This was the point where uranium became not just an element of the Earth, but a cornerstone of the atomic age. In 1951, the potential of enriched uranium was put to the test when the experimental breeder Reactor 1 in Idaho lit up 4 small light bulbs, the first electricity ever produced from atomic energy. Just 3 years later, in 1954, the Obninsk power plant in the Soviet Union became the first station to connect nuclear power to the electrical grid using uranium enriched to around 5%. This was the dawn of civilian nuclear energy. Today, enriched uranium provides about 10% of the world's electricity, a remarkable achievement that shapes the lives of billions. But how exactly does uranium move from being a rock buried deep underground to becoming the polished fuel that powers reactors? The journey begins in some of the most remote landscapes on Earth, vast deserts in Australia, open plains in Kazakhstan, and rocky terrains in Canada supply about 70% of the world's uranium. Here the element is locked inside minerals like uraninite, often called pitchblende. These ores may only contain uranium in concentrations as low as 0.1%, sometimes up to 2%, but that small fraction is enough to fuel nations. To extract it, massive excavators carve away layers of earth in open-pit mines, exposing the rock for processing. In other regions, miners tunnel deep underground, sometimes hundreds of meters below the surface, to follow uranium-rich veins. There is also an innovative method called in situ leaching, where chemical solutions such as sulfuric acid or carbonates are injected into the ground to dissolve uranium directly from the deposits. The dissolved uranium is then pumped back to the surface, sparing the need to dig giant pits or tunnels. No matter the method, once uranium is extracted, it must be transported to processing facilities for the next stage. At these plants, the ore is crushed until it resembles coarse sand, a texture that allows chemical treatments to separate uranium from the other minerals it is mixed with. The crushed ore is then placed into large steel tanks and mixed with strong acids or alkalis that leach out the uranium. What emerges from this complex process is a bright yellow powder called yellowcake, or uranium oxide. Despite its harmless appearance, this powder contains about 80% pure uranium. It has a faint metallic smell, and while its radioactivity is relatively low, it is still dangerous to breathe in. So workers wear protective suits, masks, and use specialized ventilation systems. To give a sense of scale, 1 ton of yellowcake can produce the same amount of energy as several million tons of coal. It is at this stage that uranium truly starts to reveal its extraordinary energy potential. From the processing plants, yellowcake is sent to conversion facilities. Here, it is transformed into a chemical compound called uranium hexafluoride, often abbreviated as UF6. This compound is especially important because it can switch between solid, liquid, and gaseous states at relatively low temperatures, which makes it perfect for the enrichment process. Conversion begins with purification, removing impurities like sulfur, magnesium, or other trace metals. The purified uranium is then exposed to hydrofluoric acid in sealed reactors, producing uranium hexafluoride gas. At room temperature, it can solidify into crystals that technicians sometimes call nuclear snow because of its pale greenish appearance. It's a compound that requires extreme care as it reacts violently with water to form toxic substances. For this reason, conversion plants are equipped with corrosion-resistant equipment, advanced ventilation, and sensors that can detect even the smallest leaks. Now comes the most critical step of all: enrichment. Uranium hexafluoride gas is fed into tall cylindrical machines called gas centrifuges. These centrifuges are technological marvels made of ultra-strong alloys and carbon composites. They spin at over 50,000 revolutions per minute inside vacuum chambers that reduce friction. As the gas spins, centrifugal force pushes the heavier uranium-238 isotopes outward while the slightly lighter uranium-235 collects closer to the center. This separation process is delicate, and even the tiniest imbalance, just a few milligrams of weight, can damage the centrifuges. To prevent this, each one is monitored by seismic sensors and real-time control systems that adjust their speed with incredible precision. A single centrifuge can process tons of uranium hexafluoride in a year. But enrichment facilities don't just use one machine. They use cascades, hundreds or even thousands of centrifuges connected together, each one making the uranium a little bit richer in U-235. These cascades often fill entire buildings and run non-stop for decades, producing uranium enriched up to around 5% for commercial reactors. The enriched uranium gas is then converted back into a solid form. Through carefully controlled chemical reactions, it is turned into uranium oxide powder once again. This powder is pressed into small, dense pellets, each one about the size of a fingertip. Despite their tiny size, these pellets are powerful. One of them contains as much potential energy as a ton of coal. To make them reactor-ready, they are baked in furnaces heated to around 1,400 degrees Celsius. Forming tough ceramic materials that can withstand the intense heat and radiation inside a nuclear reactor. The pellets undergo strict quality control. X-rays scan for microscopic cracks, laser scanners measure dimensions to micrometer precision, and spectrometers check for impurities that could interfere with nuclear reactions. Once approved, the pellets are stacked inside long tubes made of zirconium, a silvery metal that resists heat and corrosion while allowing neutrons to pass through. Each tube or fuel rod contains around 400 pellets stacked precisely. Robots handle this process inside clean chambers to avoid contamination. Finally, dozens of fuel rods are bundled into fuel assemblies, carefully welded and tested until they meet exacting standards. These assemblies weigh around half a ton each, and just one of them can power 100 homes for an entire year. When the assemblies reach a nuclear power plant, they are placed inside the reactor core. A single reactor might hold nearly 500 of these assemblies, totaling thousands of fuel rods. Here, the magic of nuclear energy truly begins. Inside the core, uranium-235 atoms split apart when struck by neutrons, releasing tremendous amounts of heat and more neutrons that sustain a chain reaction. The energy released by splitting just one uranium atom is millions of times greater than burning a single carbon atom in coal. To keep the reaction under control, control rods made of materials like boron or cadmium can be lowered into the core. These rods absorb neutrons and act like brakes, slowing or stopping the reaction when needed. The entire system is surrounded by reinforced concrete walls, some as thick as 2 meters, designed to withstand natural disasters or even direct impacts. Inside, automated systems monitor temperature, pressure, and neutron activity constantly, ready to shut everything down if the slightest irregularity is detected. The heat generated from fission doesn't just sit in the core. It is used to boil water, creating steam under high pressure. This steam is channeled into massive turbines that spin at nearly 1,800 revolutions per minute. The turbines are connected to giant generators, which transform the mechanical motion into electricity. A single reactor can produce more than 750 megawatts of power, enough to supply 500,000 homes with electricity. Unlike coal plants, which spew smoke and ash, nuclear reactors emit almost no carbon dioxide while operating, making them one of the cleanest large-scale energy sources available today. Make sure to give the video a like, share it with someone who loves science and technology, and subscribe for more content like this. What are your thoughts on the role of nuclear energy in the future? Leave a comment below, and let's continue the conversation. There's something almost unreal about the first time you see it. At first, it's just a thin glimmer in the distance, a silver blade rising from an ocean of golden sand. But as you draw closer, it stretches upward endlessly, slicing into the clouds as if it's trying to touch the edge of space itself. That's the Burj Khalifa. More than a building, more than a record breaker. It's a message written in glass and steel, a statement that says, humanity doesn't just build to survive, we build to dream. Yet, for all the headlines about its staggering height, the most extraordinary thing about the Burj isn't how tall it is. It's what covers it. Wrapped around this superstructure is a second skin, a shimmering glass armor designed to battle the elements of the desert. Because here, in a place where summer temperatures soar above 50 degrees Celsius and sunlight hits like a hammer, building tall is one thing. Making it livable is another challenge entirely, and solving that problem would push science, engineering, and design to their absolute limits. To understand how this tower came to exist, you have to rewind to a time before it dominated Dubai's skyline, a time when the city was more ambition than reality. In the early 2000s, Dubai was a rising power with a looming problem. Its wealth still relied heavily on oil, and everyone knew that oil wouldn't last forever. The city needed a new identity, something iconic, something permanent, something that would draw the eyes of the world. So its leaders came up with an idea that bordered on impossible: build the tallest structure humanity had ever dared to imagine. Not just taller than anything that came before, but beautiful, futuristic, and impossible to ignore. Construction began in 2004. 6 years later, the world watched in awe as the Burj Khalifa officially opened, 2,717 feet tall, 163 stories high, and visible from nearly 100 kilometers away. But once the steel and concrete were in place, the real challenge began. How do you protect a structure of that size from the brutal desert climate? How do you create windows that can withstand scorching sunlight, hurricane-force winds, and drastic temperature changes, yet still remain crystal clear for those sweeping views of the Arabian Gulf? The solution began with something that feels almost poetic: sand. The very substance that defines the desert became the starting point for the building's armor. But not just any sand, ultra-pure quartz, mined and refined to perfection. It was mixed with soda ash and limestone in precise, carefully guarded proportions. That mixture was then fed into a furnace the size of a small house, where it was blasted with heat exceeding 2,700 degrees Fahrenheit. Inside, a remarkable transformation took place. The dull, gritty sand melted into a river of glowing orange liquid, molten and alive, flowing like lava. This was the birth of the Burj Khalifa's glass. But turning that molten stream into flawless panels wasn't a simple task. The molten glass was gently poured onto a bed of liquid tin, a process known as float glass manufacturing. Because glass is lighter, it spread perfectly across the tin's surface, forming a smooth, uniform sheet without rollers or imperfections. It was like watching a sheet of liquid light settle into place. Yet even then, the work wasn't done. If the glass cooled too quickly, internal stresses would cause it to shatter under pressure. So it was slowly and carefully cooled in a long tunnel, a process known as annealing, which stabilized its structure and gave it strength. Once cooled, the glass underwent one of the most advanced processes in modern engineering: magnetron sputtering. Inside a vacuum chamber, atoms of silver and other metals were fired onto the surface of the glass, building up invisible layers measured in nanometers. These microscopic coatings completely changed how the glass behaved. They reflected infrared radiation, keeping the desert's brutal heat outside. They blocked ultraviolet rays, protecting the interior from fading and damage. And yet, they still allowed visible light to pour through, filling rooms with natural daylight and preserving the breathtaking views. The transformation continued as the glass was reheated to around 1,150 degrees Fahrenheit and then blasted with cold air, a process called tempering. This rapid temperature shock compressed the surface, making the glass up to 5 times stronger than ordinary windows. And if it ever did break, it would crumble into small, harmless pieces instead of dangerous shards. Finally, 2 sheets of glass, one coated, one laminated, were fused together with a thin spacer in between, forming a sealed cavity. That space became a powerful thermal barrier, locking the heat out and the cool air in. The result wasn't just a window, it was a piece of environmental technology. Of course, creating this advanced glass was only half the battle. Installing it on the tallest building on Earth was another story entirely. Each panel weighed hundreds of pounds, and more than 26,000 of them had to be lifted and attached with millimeter precision, hundreds of meters above the ground. Specialized cranes hoisted the panels into position, while teams of workers, often suspended from harnesses high in the sky, guided them into place. More than 12,000 workers contributed to this monumental task, investing over 22 million hours to assemble the Burj Khalifa's shimmering exterior. And once installed, the glass didn't just sit there, it worked. In Dubai's humid climate, condensation forms naturally on the panels. Most buildings would simply let it evaporate. The Burj Khalifa, however, captures and collects it. The building channels this water into storage tanks, harvesting roughly 15 million gallons every year, enough to water all the gardens surrounding the tower. The structure isn't just standing in the desert, it's interacting with it, turning nature's challenges into resources. What began as sand now acts as a shield, one that reflects light, regulates temperature, blocks radiation, and even gathers water from the air. It's more than glass, it's a living skin, a technological armor that makes it possible for people to live and work comfortably in a place that should, by all logic, be inhospitable. And it's a perfect metaphor for what the Burj Khalifa represents: the idea that human ingenuity can reshape the natural world, bending it into something that serves our ambitions instead of standing in our way. But the story of the Burj Khalifa's glass isn't just about engineering brilliance, it's also about how far humanity is willing to push its own imagination. Because when you peel back the layers of that shimmering facade, what you're really looking at is a philosophy, one that's repeated across countless industries and inventions. It's the idea that raw, messy materials from nature can be transformed into something refined, purposeful, and world-changing. We've done it for centuries. Sand into glass, iron into steel, crude oil into fuel. The pattern is the same. We take what the Earth gives us in its most chaotic, unrefined form, and through science and ingenuity, we shape it into something that powers our cities, connects our continents, and redefines what's possible. The Burj Khalifa is just one, albeit spectacular, expression of that story. It's a concept you see clearly when you compare glassmaking to another cornerstone of the modern world: oil refining. Deep in the heart of Texas, vast refineries receive shipments of crude oil, thick, black, and unusable in its natural state. It's heated, distilled, broken apart, and recombined into products that power planes, cars, and industries. It's a transformation that turns a worthless raw substance into the lifeblood of modern civilization. And in many ways, the process mirrors what happens inside a glass plant. Both take elemental resources and, through extraordinary precision, elevate them into something extraordinary. That's the deeper story hiding behind the Burj Khalifa's reflective skin. Each of those 26,000 panels is more than a construction material. It's a triumph of chemistry, physics, and design. It's proof of what happens when thousands of small decisions, the right sand, the right coatings, the right temperature, the right installation techniques come together in perfect harmony. And it's proof that no dream is too ambitious if you're willing to solve 1,000 small problems on the way to achieving it. Every detail of the Burj Khalifa's design reflects this mindset. Even its Y-shaped floor plan, inspired by a desert flower, is about more than aesthetics. It channels wind around the structure, reducing pressure and preventing the kind of vortex shedding that could make a tower sway or vibrate uncontrollably. The building doesn't just resist the elements, it collaborates with them, shaping and redirecting their forces. The same principle applies to the glass. Its coatings don't merely block sunlight, they manipulate it. Infrared wavelengths are reflected outward, ultraviolet light is filtered, and visible light is diffused in just the right way to illuminate the interiors without overheating them. The panels don't just stand there passively, they're actively working every second of every day to maintain the tower's delicate internal environment. And while they're doing that, they're also collecting and redirecting water, millions of gallons of it each year. What would otherwise evaporate into the desert air is captured and put to use, watering the landscaped gardens that surround the tower and softening the harshness of the environment. This isn't just clever engineering, it's a subtle form of sustainability. In a region where water scarcity is a daily concern, the Burj Khalifa quietly demonstrates how even the most iconic structures can help sustain the ecosystem around them. That attention to detail extends far beyond the materials themselves. The installation of the glass panels was a logistical operation as complex as the Apollo missions. Each panel had to be manufactured, shipped, lifted, and secured in an order so precise that even a single mistake could compromise the building's performance. Wind loads, thermal expansion, alignment tolerances, every variable was calculated down to fractions of a millimeter. The result is a facade that isn't just strong and beautiful, but perfectly integrated into the building's structural system. And perhaps the most fascinating part, even after all these years, the Burj Khalifa's glass is still doing exactly what it was designed to do, and doing it flawlessly. The tower remains cool and habitable in one of the hottest climates on Earth. Its interior spaces are flooded with natural light without becoming ovens. Its reflective surface still gleams under the desert sun, as striking now as it was on the day it opened. When people visit the observation deck and gaze out over Dubai's skyline, they're usually thinking about the view, about the sheer height, the endless city below, the Persian Gulf stretching into the horizon. What they don't realize is that the only reason they can stand there comfortably, hundreds of meters above the ground, is because of the invisible science all around them. Every ray of sunlight they see, every gust of hot desert wind that never makes it inside, every drop of condensation that's quietly collected, all of it is the result of deliberate, meticulous choices made decades earlier. And that's the deeper beauty of the Burj Khalifa story. It's not just a tale about building the tallest tower. It's about humanity's refusal to accept the limitations of nature as they are. It's about solving problems that once seemed unsolvable, not by brute force, but by creativity, precision, and persistence. It's about looking at something as simple as sand and deciding it can become something extraordinary. When the Burj Khalifa opened in 2010, it was hailed as a symbol of wealth and ambition. But if you look closer, you see something much bigger. You see the fingerprints of thousands of people across continents, scientists, engineers, designers, and workers, each contributing their expertise to a single vision. You see the fusion of ancient knowledge and cutting-edge technology. You see a structure that doesn't just defy gravity, but also climate, physics, and time. And perhaps most importantly, you see a promise. A promise that no matter how extreme the environment, how audacious the dream, or how impossible the goal, there's always a way forward if we're willing to innovate. The Burj Khalifa isn't just a skyscraper, it's a testament to what humanity can achieve when ambition meets ingenuity. So the next time you see that iconic spire gleaming against the desert sky, don't just think of it as the tallest building in the world. Think of it as a story told in glass. A story of transformation, collaboration, and relentless curiosity. Think of the sand that became glass, the glass that became armor, and the armor that became a beacon of possibility. Because in the end, that's what the Burj Khalifa truly is. Proof that the impossible isn't a wall, it's a starting line. If stories like this fascinate you, the ones hidden beneath glass and steel, where science meets imagination and engineering turns into art, Then don't stop here. There are countless more creations around the world with secrets waiting to be uncovered. So stick around, hit that subscribe button, and join us as we explore the extraordinary ideas shaping our future, one masterpiece at a time. Because behind every skyline and every invention, there's a story. And we're just getting started.